Welcome to Business Analytics. My name is Hari Rajagopalan and I will be your instructor for this section. In this section, we are still in Descriptive Analytics, and what we're going to discuss in this video is on sampling and how we're going to calculate probabilities when you have sampling. So we are right here in Descriptive Analytics, and a lot of the stuff we are discussing here will be used in predictive and risk analytics. So let's talk about standard deviation. Remember, when we first started talking about standard deviation, it was a measure of dispersion or variance or variability, right? It's how your data is spread out, and it's essentially the average distance from your mean. So for example, if I said, if you graduate with an MBA, your average salary is $6,000, standard deviation of 1,000, that means that you expect to get about 6,000 on average, but sometimes you get more, some people get more, some people get less. And the average amount you get more or less is about $1,000. And that's essentially what standard deviation is. So population standard deviation is essentially the data in the population and calculate the standard deviation. That's sigma. Sample standard deviation is you take all the data in the sample and calculate standard deviation, and that's denoted by S. So remember, there's a difference between population and sample, and you've probably heard this in the previous lecture. You also heard about standard error or standard deviation of sample means. Now, this is when you take multiple samples from the population. Each of those samples with a sample size has a sample mean. And if you look at the distribution of data of those sample means, they have a standard deviation, and that's called standard error. And an estimation of this standard error is given by population standard deviation divided by square root of sample size. And often it is given in the textbook as sigma x bar. There's a bar here which is really small, but it should be a full bar over that x. So how do you calculate probabilities for sample means? So we're going to use the Excel formula norm.dist. The probability of getting less than a value of a given with a given mean and standard deviation. So let's assume that we have a population with a mean and standard deviation. You're given a value. You're going to use norm.dist. You're going to put that value. You're going to put the mean. You're going to put standard deviation. And you're going to put true for cumulative because we are looking at cumulative values. Or you can calculate the z-score using this formula, value minus mean divided by standard deviation, and plug in the z-score. Z-score gives you the number of standard deviations from the mean. So value minus mean is distance from the mean divided by standard deviation gives you number of standard deviations. So probability of getting less than a sample mean given population mean and population standard deviation in Excel. Now look at the difference between this, the first one and the second one. The first one is talking about a single value. The second one is talking about a sample mean for a group of data. So if you are looking at probabilities for sample means, there is a slight change in the standard deviation. So you're going to use norm.dist just like you did, but you'll use sample mean. Of course, this will be the population mean. And here, instead of using standard deviation, you will use standard error. Now, since in any kind of analytic situation, any kind of tests you're going to learn, you're going to use samples and sample means, you are usually going to use standard error and not standard deviation. So remember, standard error is population standard deviation divided by square root of sample size for normal distribution. So let's take an example and contrast it with another example where we are using sample means. In this example, we are going to use a single value taken from a population. So assume that average salary for business students is 40,000 and standard deviation is 5,000. When a statement like this is made, you can kind of be sure that these values are population values. So population mean is 40,000, standard deviation is 5,000. And the probability that one MBA student randomly selected will have a salary less than 33,000, more than 33,000, less than 48,000, more than 48,000, and then there's between these two values. So here are the questions asked. And it could be any other number. It doesn't have to be 33 and 48. It could be any other number here. But these are the questions you ask when you have a value from a distribution. You want to know what's the probability. So given that it's the value of a single student or the salary of a single student, we can use this standard deviation that we have, plug it into Excel, use norm.dist, put the value in x, the mean, standard deviation, and true, and get the value. That gives you the probability it's less than the value, norm.dist. And if you want probability of it being more than a value, you need 1 minus this value. Now, you can go ahead and finish the rest. But remember, when you do part E, if you have to find the probability it's between 44,000 and 34,000, you would need to first find the probability it's less than 44,000, just like we did here, and then find the probability it's less than 34,000 and subtract the two values. Now, if you have samples on the other hand, let's take the same example, and instead of having one MBA student, you're selecting 100 MBA students, and you have a sample mean here. And you want to find out the probability that the sample mean is less than 39, more than 39, and so on, right? So you have a list of different values, but this has got nothing to do with one MBA student. This has got to do with a group of MBA students, and you're looking at the sample mean here. So you cannot use the standard deviation here. You will have to use standard error. So standard error, remember, is the standard deviation of the sample means. And so you are going to have to calculate the standard error, which is 500. Notice that the standard error is much smaller than your standard deviation. If you have a sample size of 1, then standard error and standard deviation are the same thing, because it's just like selecting one person, right? But since you're selecting more than one person, your standard error will always be less than your standard deviation. And this basically means that the spread, or how dispersed your data, is going to be much smaller. And that makes sense, right? If you are going to select 100 students from this group, their sample mean will be somewhere close to 40,000. So you might get higher than 40,000 or lower than 40,000, but you will get values close to 40,000. And if you get values close to 40,000, then obviously the standard deviation of those values close to 40,000 will be much smaller. So you can complete the rest using norm.distance. Just pay attention to the fact that instead of putting 5,000 as your standard deviation, you'll be using 500, which is your standard error. Now let's look at the same issue for binomial distribution. So let's take an example here. We say on average 20% of the people who are sent advertisements in their mail look at their mail. I just throw it into the trash bag as soon as I know it's an advertisement. So obviously this is a binomial distribution because you have two outcomes. You either look at the ad or you don't look at the ad. And the population proportion is 20% because 20% of them look at the ad. Now if we randomly select 100 people from the population, we can then look at the probability that the percentage of people in the sample, this 100, will see the advertisement is, and you can have a series of values here. Here we are looking for questions like, what's the probability 19% of them are going to look at the advertisement, or more than 19%, or 22 here, or between 17 and 24. So you will have to calculate standard error for population proportion, and it has a separate formula than normal distribution. So here's the standard error, population proportion multiplied by 1 minus population proportion divided by sample size. And you're taking the whole square root here. So you get 0.04. is the standard error, or 4% is your standard error. So now when you use norm.inv, you're going to put the sample proportion, which is 0.19, population proportion, and the standard error to get your, in this particular case, the probability you're going to get less than 19% is 40.124%. And you can use the same method. For B, you're going to do 1 minus 40.1294, right? And continue on. Now let's look at the last example. Now let's assume that you're given this data. Average salary for business students is 40%, and you don't have the standard deviation. So you only have population mean, you have no standard deviation. If you have no standard deviation, how are you going to calculate standard error? Remember, standard error is population standard deviation divided by square root of sample size. If we don't have population standard deviation, then we are going to use the standard deviation, which we can calculate from that sample. So instead of saying population standard deviation, we use sample standard deviation divided by square root of sample size. This creates more problems because this sample standard deviation, while it may be close to population standard deviation, if you select things randomly, it's not going to be the same. So this creates another error. You're going to get another error, which is the difference between sample standard deviation and population standard deviation. So you cannot use z-scores in this situation. Remember, z-scores require you to have the population standard deviation. We will use something called a t-score. Now, t-score is also number of standard deviations away from the mean, just like z-score was. But it compensates for the error that is created when we are using sample standard deviation to calculate standard error. So t-scores will change when sample size changes. And t-scores will be equal to z-scores when you have very, very large sample sizes. In fact, if your sample size is equal to the population size, then t-score and z-scores will be equal. So let's look at t-score examples with samples. So assume that the average salary for a business student is $40,000. That's all that is given. And now you're selecting 36 MBA students randomly. And this sample standard deviation, that is the standard deviation of these 36 MBA students, is 6,000. And so you're then asked to calculate a bunch of probabilities for different sample means. And so here you will use the sample standard deviation to calculate the standard error, which comes out to be $1,000. And then you're going to use the t-score. You use t.dist. Here that value x, in Excel, t.dist requires you to give x degrees of freedom, and cumulative is always going to be true here. And the x is actually your t-score, which you use the formula of sample mean minus population mean divided by your standard error. And degrees of freedom is always going to be sample size minus 1. So once you have this information, why don't you go use t-dist and finish the rest of the score. So for 39,400, the t-score is going to be negative 0.6. Plug those values into this equation, and you will get 27.6186%, and you can calculate the others. Now remember, in the last video you talked about confidence intervals, and we talked about z-scores, we talked about binomial distributions, but we never showed how to do a confidence interval with t-scores. So let's talk about, if we do take a sample and we don't know the population standard deviation, how are we going to build confidence intervals? So imagine sampling 100 days for fuel prices in South Carolina. You know that the sample mean is 1.92. Now, all you know is the sample standard deviation of 10 cents, and you're asked to build a 95% confidence interval. So here we, of course, have to calculate standard error, and then you're going to find the z-score. Remember, 95% confidence, you'll be looking at 2.5% and 97.5%. The t-score with 99 degrees of freedom for 2.5% is negative 1.98, and for positive 97.5% and 99 degrees of freedom is 1.984. Again, you can look at this as negative, this is positive. Degrees of freedom is sample size minus 1. And so you can build your confidence interval by taking 1.92, which is sample mean, plus minus margin of error. And margin of error is your z-score multiplied by standard error, which gives you this confidence interval. Now we will stop with this for this lecture. In the next lecture, we'll talk about how you can use sampling and figure out what kind of sample size you need to do a particular test.